Hello, welcome to Vlogs. In this video, I'm going to show you how I built a fraud detection model using gradient boosting, and more importantly, I'll show you the traps I fell into along the way. You see how a model can achieve near-perfect ROC AUC and still be practically unusable, how simulated data can trick you into overconfidence, and how production considerations inform how you engineer features. Fraud is a classic example of extreme class imbalance. Even though fraudulent transactions make up a very small proportion of all transactions, they can cause huge financial and emotional harm. So our goal here is to identify suspicious behaviors early while minimizing disruption to legitimate users. I'm using the PaySim dataset, which contains over 6 million rows of simulated bank transaction data. It's time-stamped with a time step, also includes origin and destination account IDs, type of transaction, amount, balance before and after transaction at origin and destination, and whether that is a fraudulent transaction. And any transaction amount greater than 200K has been flagged as risky. There are other datasets with real transaction data out there, but their features are usually anonymized as V1, V2, and it's a bit hard to understand what exactly we're working with. I downloaded the dataset from Kaggle, loaded it into a data frame, and did some basic sanity checks, such as previewing the head, checking the shape and data types. I did some light exploratory analysis. The goal here is to make sure the data is clean enough and to inform modeling choice. There's no need to over-clean simulated data, and we're not trying to uncover new business insights or create beautiful charts. So I just checked for missing data. There was none, as expected for a simulated dataset. Checked class imbalance. We can see that fraud class is highly imbalanced, like in the real world, making up 0.1% of all transactions. So it's important that when we evaluate our model, we don't just look at ROC AUC, but also check precision recall AUC. I'm going to explain this further when evaluating our model. I also checked the count of fraud by transaction type, and among outward transactions, we can see it's much higher in transfer and cash out than in payment, so we know type is an important signal to help the model learn. And this is the distribution of transaction amount for fraud and non-fraud. By checking the mean and the percentiles, we can also get a feel that fraud tends to concentrate in bigger amounts, although there is substantial overlap. I also checked fraud distribution over time. There's clearly an increase after time step 400. This might be too clear-cut because it's a hard-coded rule in the simulated dataset, but in reality, fraud patterns can definitely evolve over time. Scammers can get sneakier, and all of a sudden equipped with AI, models trained on past data might not always give correct predictions in future. So it's important that we monitor changes in data, performance of models, and retrain when appropriate. Then we move on to feature engineering. I'm planning to use a tree-based model which splits on thresholds. Since it doesn't depend on distance, there's no need to scale our features. Also, I'm planning to use LightGBM, which handles categorical features nicely. There is no need to one-hot encode features like type of transactions. We just need to cast it as category. This way it's memory efficient too. Here it's important that we don't also cast or encode the account IDs. These are extremely high cardinality features, meaning they contain a huge amount of unique values. One-hot encoding them would create very sparse and noisy vectors that don't help the model learn, and any new ID unseen by the model could break the logic. Essentially, fraud is based on behaviors, not identity. IDs don't generalize. Including them will only cause leakage and overfitting. Another thing I've done is log transforming the transaction amount. It's not strictly necessary since, as I said, we're using a tree-based model and there's no need to scale, but our data is heavily skewed with a long tail, so I'm hoping the log transform could help the trees find better splits, reduce dominance of extreme outliers, and stabilize feature importance. I'm not replacing the original amount though, I'm keeping both and letting the model decide. It would really help the model learn if we give it more context, such as pre-calculated ratios. I've added transaction amount to account balance ratio to our dataset. If this is 1, that means all the money in an account is being moved, and in an outbound transaction, that could potentially be dodgy. I've also added rolling temporal or velocity features per account, so the model knows not just about the current transaction, but what happened leading up to this transaction. To do that, I've first sorted the data by origin account and time step, and calculated total transactions originating from an account in the last one step in time. We could assume that's 1 hour in the simulated dataset. I'm doing this because fraud often have a burst pattern, with lots of activities happening in a short amount of time. Imagine a credit card thief trying to make as many purchases and as quickly as possible before you lock the card. I've also calculated total transactions in the last 5 time steps to capture more sustained suspicious behaviors. And 5 could be 10 or 24 depending on your business scenario. I've also added how the current transaction amount compares to the average of the past X number of transactions, because if there is suddenly an amount much larger than normal, that's a red flag. I initially hard-coded past 5 transactions, but then you can see I quickly checked here that our simulated data only has up to 3 transactions per account. So I've made it a variable and we can define the window size based on business needs in real life. I've also calculated the ratio of cash outs and transfers in the last X transactions, since fraud often concentrates in these actions. We could add calculated features grouped by destination accounts too, which should help us identify accounts consistently involved in suspicious transactions. But in reality, this information may not always be available in real time, as it might be an account from another bank. Also, for this project, the fraud rules in the simulated data might not be sophisticated enough to justify it, and including them would be extra slow. You can't see it, but it already takes more than 2 hours to process these feature engineering steps. I'm aggregating them offline and from scratch because I'm prototyping and training the model for the first time. In production, the model needs to identify fraud and block it in, according to ChatGPT, milliseconds, quicker than a blink of an eye. If we did this in production, the scammers would have drained your account, transferred the money to Cayman Islands, 12 other places, and probably back to your country, long before this calculation finishes. So in production, we would have the current states of these behavioral velocity features saved, for example, in Big Table, and when a new transaction comes in, we will have a process, for example, in data flow, to incrementally update these aggregates in near real time, before that data point is passed through the model to make a judgment. But in binary classification use cases where decisions don't have to be made in real time, such as medical diagnosis and customer booking propensity, we can batch process new data daily or weekly, and BigQuery should be sufficient to recompute the features at the required cadence. Then on to training the model. I first removed the high cardinality ID fields, as well as the above 200k flag, since it's a simple rule that doesn't add much useful signal beyond what we already have. I then sorted the data by time, and based on timely order, we split the data into training, validation, and testing. The testing set is also what we will be using to simulate production. Oftentimes, If the data is imbalanced, I would consider stratified sampling, which essentially means splitting my data into training and testing while keeping the proportion of fraud and non-fraud roughly the same. This way, the model is more robust, accurate, and fair. But in fraud detection, time matters more than stratification. In reality, models are always trained on past data to score future transactions. Stratification would mix past and future and leak information across time. The results might be unrealistically good. We then separate our features and target. In terms of model selection, my first choice was LightGBM. It's a gradient boosting tree-based algorithm. It works well on tabular data, provides built-in support for handling class imbalance, is fast and relatively easy to explain. A decision tree is like a game of 20 questions. We keep asking yes or no questions until we get each final group to only contain or mostly contain the same things. For example, one group to mostly contain fraudulent transactions and another group to mostly contain legitimate transactions. Gradient boosting then takes this further by building many small trees sequentially, with each tree attempting to fix the remaining error left by the previous one. After many such attempts, the remaining error is reduced to a minimum. We can think of it as a student who got many questions wrong in an exam, and several teachers came in, each helping them correcting one of the wrong answers. LightGBM grows trees leaf-wise, meaning instead of growing all branches evenly, it will always choose to split the branch that reduces error the most, and keep diving deeper. A simple way to think about it is like sorting Lego bricks. Instead of sorting every pile and go around again and again, you just focus on picking the messiest pile and sorting that one further. This makes LightGBM very fast and efficient, especially on large datasets, but also makes it prone to overfitting, as it could pick up noises unique to the messiest pile, which are not generalizable. Here you will notice I've set num leaves to 64. This is the maximum number of leaves in each tree, which controls model complexity. More leaves could capture more complex patterns, but might lead to overfits. I've also set my minimum data in leaf to 200 to prevent the model from creating rules based on too few samples, which might not generalize. I've also specified that my data is imbalanced, and we will apply early stopping to help prevent overfitting. Now we train the model, make predictions using our validation set, and print out the ROC AUC and precision recall AUC. There are lots of videos on YouTube that thoroughly explain how these metrics are calculated, so I won't go into too much detail. Essentially, ROC AUC is a commonly used metric to evaluate the performance of a binary classification model. It tells us whether our model consistently ranks fraud above genuine transactions. Here we've got an extremely high score of 0.999, meaning 99.9% of the time it's giving a fraud transaction a higher score than a genuine transaction. So the model is fundamentally good at separating fraud from non-fraud. This excellent result is kind of expected because fraud in our data is synthetic and generated based on rules. In reality, this would be much lower. But with imbalanced data, you can have a great ROC AUC, yet give too many false alarms, which in our case comes at the expensive cost of annoying our normal customers. So I've also examined precision recall AUC to understand how well we're balancing catching all the fraud versus not accidentally blocking genuine transactions. This metric tells us whether the model is actually usable when fraud is rare and false alarms are costly. Given a fraud base rate of 0.1%, which we've established as ground truth based on our exploratory analysis, A PRAUC of 0.23 represents a 230 times lift over random, indicating the model strongly concentrates fraudulent transactions near the top of the ranking, which is what we want. I also plotted the precision recall curve, which lets us inspect this trade-off of catching bad guys and leaving good people alone at different thresholds. For example, do we want to mark all transactions scoring 0.9 or higher as fraudulent and everyone else as legitimate? Or do we want to draw that line at 0.95? In reality, this will inform thresholds and have an impact on alert volumes and customer experience. But we can see our PR curve appears almost step-like rather than smooth. This is likely because it was constructed from only a few distinct scores instead of a smooth, continuous spectrum of scores. It can happen when we have highly imbalanced data and very sharp, raw-like fraud patterns in our simulated data. The model might have learned only a few strong discriminative signals, tested a handful of fraud probability scores, quickly saturated, and assigned these almost identical scores to most transactions. Or it could be we were too harsh with our model parameters, trying to limit tree growth to prevent overfitting. This is a good example where classic metrics like ROC AUC can look deceivingly good because it only cares about ranking, not spacing. PRAUC also does not require well-calibrated probabilities to look good, and the issue is only exposed when we examine the PR curve. This doesn't mean the model is broken. The ranking is still good, but threshold granularity is too coarse to be used in actual fraud detection. Upon further diagnosing, we can see that the model only performed one boosting round, trained one tree, produced 6 unique scores, and just stopped learning. No wonder training was so fast. So I tried retraining the model. This time we'll try smaller leaves and fewer samples in each leaf to encourage more tree growth. I've also supplied the exact ratio of non-fraud to fraud to force the model to care about minority class. And I've increased the learning rate to encourage more aggressive learning and faster convergence. We're still relying on early stopping to prevent overfitting. This time we can see the model has had 5 rounds of boosting, or in other words, created 5 trees. It's produced 26 unique scores, which is an improvement on 6, but the PR curve is still near linear with weak separation power. In reality, we need more fine-grained probability estimates to draw our thresholds. The model behaves this way because, like I explained earlier, tree growth in LightGBM is leaf-wise, which is faster but more aggressive compared to, for example, XGBoost. It also pre-bins features into histograms, searches for splits between bins instead of individual values, which also makes it faster. When this meets extreme signals in simulated data, LightGBM found only a few meaningful splits that separate fraud from non-fraud. Further splits didn't improve ranking, resulting in very early stopping and coarse output granularity. So to make our model more usable, instead of using LightGBM, I've decided to switch to XGBoost. The key difference is that XGBoost grows trees level-wise as opposed to leaf-wise. Back to our Lego sorting example, this means we're sorting round by round, and in each round we will go through every pile. So XGBoost tends to produce more gradual refinements and finer-grained score distributions. Here we've trained the XGBoost model, and after evaluating on our validation set, we can see that not only our ROC AUC is excellent, our PR AUC is also amazingly good at 0.905, and the PR curve is more what we'd expect. I've also examined feature importance. Unfortunately, this doesn't show the feature names, but it initially told me that my model relied quite heavily on the time step itself. Thinking about it, since we have derived temporal features and are not using a sequence model, the time step itself is not causally meaningful. And since we know fraud density changes over time in PaySim data, it might introduce spurious signal. So what we're seeing here is actually after I'd removed it and retrained my XGBoost model. The feature importance chart also tells us that native features appear to be more important than our aggregated ratios, temporal and velocity features. So out of curiosity, I've also benchmarked against an XGBoost model trained on native features only. And ROC is indeed even better at 0.94. This is likely because in PaySim data, fraud is based on simple rules such as large amounts, draining accounts, etc. Native features already capture these signals, and temporal and velocity features do not add much signal, only noise. In real-world fraud detection, however, temporal and velocity features are often critical because fraud patterns evolve and manifest over sequences rather than single transactions. We might even need to consider using more complex, sequence-based deep learning algorithms to train our model. Now I'm going to go back to my XGBoost model trained on all features and select the lowest threshold that achieves 99% recall on the validation set. And that gives us a probability score of about 0.9913. If we draw the line here and flag all transactions scoring above this, we'll catch 99.1% of the fraud transactions, and out of everyone we flag, about 40% are actual culprits, while 60% are innocent. Whether that 60% might be too much largely depends on the base fraud rate. In our validation set, out of nearly 1 million transactions, only 0.6% or roughly 60 transactions were fraud. So if we are to catch 99% of them, say 59 out of 60, we would have flagged a total of 150 transactions, including 91 innocent ones, for the human team to further check. Doesn't sound too bad, right? When the base rate is so low, but whether that is acceptable in real life is a business question. We then further evaluate our selected threshold on our test set. This is data the model has never seen before. At our selected threshold, we are catching 0.9998% of fraud, nearly all of them. And our precision has also improved to 0.77. This is a bit anti-intuitive as test scores are usually poorer. But I then checked the baseline fraud rate in our test set versus our validation set and can see it's nearly 10 times higher. This indicates that there was more fraud as time goes by, but not necessarily more complex fraud patterns. So the logic in our model still holds, and we were able to catch them more precisely. This highlights the importance of monitoring of data and model performance drift, as well as adjusting our threshold as needed. Now, happy with what we've got? I will save my training, validation, and test data, my model, the threshold we've selected, feature schema, and metadata. In the next notebook and hopefully the next video, I'm going to show you how I'll deploy the model and simulate production. So stay tuned.